In number 2, we're considering a linear transformation T from R3 to R3. The domain is 3-dimensional space, and the codomain is 3-dimensional space. You can plug in any 3-dimensional vector into the transformation, but the transformation is not necessarily onto. You may not get every possible 3-dimensional vector as an output. In fact, this transformation turns out to not be onto. It's defined by the formula that I was just talking about. T of x is a times x. When you see this kind of equation, say that kind of thing in your mind. T of x is a times x. T is a function, a is a matrix. This is plugging a vector into a function. This is a matrix times a vector. This is the formula for the function T. A is this particular matrix. Part A, show details by hand using elementary row operations to help you find the kernel of T, which is also called the null space of A. And here's the symbols for those things, but they're the same thing. In parametric vector form, show your work. Answer the question whether T is 1-to-1 or not. Explain, describe the image of T as a set of linear combinations. I didn't ask you whether T is onto or not, but it turns out to not be onto. For the sake of time, we'll use the calculator just to do the row operations for us. And I think here after exam 1 and maybe a few more homework assignments where you're dealing with bigger matrices, doing things by hand, after that point will allow you to do row operations just with your calculator. So you want to be in the matrix menu. Matrix menu on a TI 84 at least is above the x to the -1 button. Second matrix. Got your names. Go to the edit menu to actually do the editing. I want a 3x3 matrix, or maybe, I mean, you don't have to do this, but maybe I want a 4th column of all zeros. Maybe you want to do that just for clarity's sake in your own mind. Write an augmented matrix, because when you're finding the kernel of the transformation, also called the null space of the matrix, you are trying to really find the solution set of a system of equations where the right-hand side numbers are all 0. That's what the kernel is, the solution set of such a system. So it's not a bad idea to keep this as a 3x4 matrix, though you don't have to. If you, in your mind, realize you've got a column of zeros that you could imagine being there. It's a slightly different matrix than what I've got here. So 1, -3, 4, 0 for the last entry. Then 2, 2, -1, 0, 3, -1, 3, 0. So I'm again making the last column all zeros. That's not the matrix that you see here. It's a related matrix, augmented. I've added a column of zeros, because that could be helpful to remind you that you're really solving a system of equations. That's why you do it. And if you are solving it, I mean, if they're all zeros, they're not going to change under row operations. It's still going to be all zeros at the end. If they were not zeros, then you for sure would want them there. If you're solving when they're all zeros, it's called a homogeneous system. When at least one of them is non-zero, it's called a non-homogeneous system. If you were solving such a non-homogeneous system, for sure you'd want to use an augmented matrix. It's only with a homogeneous system that you don't actually have to make an augmented matrix, because the zeros don't change. So there we are. There's the matrix. If I did not make a mistake, now go back to the matrix menu, do your math. RREF is what you want. Reduced row echelon form is what that stands for. Reduced row echelon form. Nope, not there though. Got to go back to my main screen. RREF. Go back to the matrix menu again and pick the name of the matrix. There we have it in decimal form. The RREF is, I'll just write it this way in the paper. The RREF is 10.625 is the same as 5/8 if you did it with fractions. Again, I'm making an augmented matrix here. I'm going to put a 0 there. I like putting a dashed line by hand when I make an augmented matrix. On my blog, infinityisreallybig.com, visual linear algebra online, I couldn't figure out a way to make a dash line. So that's why you don't see those there. 0, 1, negative 1.125 would be negative 9/8, 0, and then all zeros. Okay, so that's what you should have gotten when you show your steps by hand. What is this equivalent to as a system of equations? First equation would be x plus 0y plus 5/8 z equals 0. Second equation would be 0 times x is 0, 1 times y is y, minus 9/8 z equals 0. You've got a free variable here because the bottom row doesn't have a 1, it's all zeros. Z is the free variable. What you want to do now is you want to solve the system for x and y in terms of z by, in the first equation, subtracting 5/8 z from both sides. And in the second equation, adding 9/8 z to both sides. So one way to write the parametric vector form of the solution set is to say, hey, z is my free variable, z is just itself, and then use these equations to write x and y in terms of z. So x is negative 5/8 z, and y is 9/8 z. The set of all such vectors as z varies over the real number system is a way to write the solution set in parametric vector form. There's a vector, and z is the parameter. The free variable is the parameter. That's why we call it parametric vector form. It's kind of like parametric equations in multivariable calculus, which you probably are learning about right now, and maybe have a test on today if you're in the class, and I'm going to be proctoring the test, by the way. It's like parametric equations. It's like the z is like t with parametric equations. Even if you're not in multi, you maybe learned about that in Calc 1 or Calc 2, parametric equations. You also could factor the z out. Like this. The set of all vectors of this form such that z is a real number would be another way to write the parametric vector form. It's also okay to multiply this constant vector by any non-zero scalar. Like maybe 8 would be a good idea. You could have gotten away with a negative 5, 9, 8 there instead, even though you see fractions up here. Because all we're after are vectors that are parallel to this times the parameter. So this would have been okay as well in the end. Does that make sense? Geometrically, what is this solution set? Geometrically, it's a line to the origin in three-dimensional space. If this is, say, the positive x direction right there, the positive y direction right there, and the positive z direction right there, and you try to draw a vector parallel to this one, say, x is negative 5, y is 9, z is 8. Well, you kind of got to use your imagination here, your 3D imagination. X being negative means you'd have to go behind the piece of paper here. Y and z are positive, so you'd go up and to the right as well. You kind of got to imagine this arrow that I'm drawing as going behind the paper in your imagination. And the solution set then is all vectors that are parallel to that line when you put their base at the origin. They're along the line. Effectively, this line is the kernel of T when thought of as a set of points. which again is also called the null space of A. Kernel of the linear transformation, null space of the matrix mean the exact same thing, because all linear transformations have matrices, and all matrices define linear transformations. Very tight connection between the two. As far as whether this transformation is onto, the answer is no. And it's good enough to say, well, you know, every point or every vector on this green line gets mapped to the origin, therefore it can't be one-to-one, because you've got infinitely many points getting all mapped to the zero vector. For example, there are other arguments you can give as well. You can find t of some other vector that's not in this line, see what it equals. It won't be the zero vector. And see if you can solve for some other vector that gets mapped to that given vector. But this is the easiest thing to say. All the points or vectors on this line get mapped to zero. There's infinitely many of them. This function can't be one-to-one. It also turns out to not be onto. What is a parametric vector description of the image of T, also called the column space of A? There's nothing much you need to do there. You just need to say, take a linear combination, the set of all linear combinations of the columns of A. Done. So this was the kernel of T, or the null space of A. The image of T, also the column space of A, by definition is the set of all linear combinations of the columns of A. Arbitrary scalar times the first column plus an arbitrary scalar times the second column plus an arbitrary scalar times the third column. That's what the column space and image, that's what it is. So you could write x times the first column is 1, 2, 3, plus y times the second column, -3 to -1, plus z times the third column, 4, -1, 3, as x, y, and z all vary over the real numbers. There's 3 parameters, x, y, and z. Looking at this, it's not obvious that this is not onto, that you're not going to get all three-dimensional space here. You've got 3 parameters. You might think that should give you all three-dimensional space. And to tell you the truth, with an arbitrary 3x3 matrix, it probably will. But I picked this matrix special. In fact, I picked this matrix so that if you take the first column, and let's see. Well, I guess I was thinking of it in terms of rows. If you take the first 2 rows and add them, you get the third row. I purposely did that. 1 plus 2 is 3. -3 plus 2 is -1. 4 plus -1 is 3. I did that on purpose so that the kernel turned out to be non-trivial. And so it's not one-to-one. And so that the column space is not all of our 3, so the function's not onto, though again, I didn't ask you about that. You got 3 parameters, and typically with 3 arbitrary vectors, this is going to be all of our 3. But these are not 3 typical vectors. They will lie in the same plane to the origin. Question? Say it again.
Since the image is 2D,
well, yeah, but you're using the fact that it's not onto, and I didn't ask you about that when you say that. The outputs of this transformation are 3-dimensional vectors. They are in R3. You got a 3x3 matrix that would get multiplied by a 3-dimensional vector. You're going to get a 3-dimensional vector. But they're not all of R3. The outputs that you're going to get will be in some plane to the origin. And I'm not going to take the time to figure out exactly how to draw the plane correctly. These 3 vectors are going to lie in the same plane when you put their tail at the origin. That's not obvious, just looking at the vectors. But this algebra confirms it.
And do we know that just because what the thing you said, what you want, what's the other use of the third row?
Yeah, I knew that would happen because of that. That's how I purposely made this matrix that way.
So like, if the matrix has that property, we know that it's going to output to the plane.
If it's a 3x3 matrix, yes. If the sum of the first two rows, for example, is the third row, then yes, it will not be onto and the image will be a plane. It will be a plane as opposed to some curved surface. Kernels and images of linear transformations have to be linear, rigid, flat, like lines to the origin or planes to the origin, or some higher dimensional version of those things with bigger matrices.